Okay, so I think let's today cover Euler's Totient function. Okay,
Yes, sir.
so the idea is, so the concept of GCD is very important to the entire study of number theory. Okay, so in number theory, I think you all know what coprimes are. So coprimes are any number, let's say A and B, such that GCD of A and B is equals to 1. Okay, so obviously any number is coprime to, given a prime P. So if P is a prime, every single number is a coprime to P, right? So now let's study this definition. Okay, so what is an Euler's torsion function? So the idea is, if we are given, okay, so if we are given any integer n, okay, not necessarily a prime P, so any integer n, we are interested in understanding how many numbers, how many integers less than or equals to n, which are co-prime to n. Okay, so that is essentially what the Euler's torsion function gives you. Okay, so Euler's torsion function says this. So phi n, it's represented as phi n GCD kn, set of all numbers k such that less than equal to such that the GCD is 1. Okay, so to ask if something is not clear. Okay, so I think in number theory this is the most important concept. Okay, I mean others are probably more difficult as well, but this is something where the actual number theory starts, in my opinion. Prior to that, it's all just number system, etc. Okay,
Yes, sir.
yeah. So for instance, if we take 12, okay, so the numbers which are co-prime to 12 are what? 1 is 2 co-prime? No, right? So 1, 2, 3 is also not, right? 4 is also not. So what you will see is 5, so 6, not 7, 9, 10, 11. That's right. So it is 1, 5, 7, 11, which is 4, right? So
Yes, sir.
co-prime to 12 is are 4 integers. Okay, which means phi of 12 is 4. Okay, now see the entire number theory as per ISI syllabus more or less boils down to the study of studying the understanding of GCD between two numbers. Okay, so let's assume there are two properties, for instance. Okay, so let's go to the properties of torsion function. So obviously, if n is a prime, so obviously we know that it will be p minus 1, right? So phi of n will be n minus 1 or p minus 1. Okay, so it's a trivial corollary from this. Okay, now two things which are very crucial. Okay, an important property. So let's first understand what. So given a prime p, it's simple, right? We know that phi of p is p minus 1. It's simple, right?
Yes, sir.
Yeah. Yeah. That is something we know. Which means, so let's go to this. What is phi of p square? So phi of p square will be, look at this way,
T
1,
square.
right? P plus 1, p plus 2, dot, 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 p square, right? Now, all of these numbers are coprime. All of these numbers are coprime, correct?
Yes,
To
sir.
p, which means p minus 1 times 2, okay? Right?
Yes, sir.
But essentially what we can see is that p square minus, sorry, uh, sorry, this is wrong. Yeah, so this is something, so the mistake that I did is actually very common mistake. Okay, so it's good that it happened. Okay, but the idea is that what people typically do, okay, p, the next number is p square, which is divisible by p, but that's not correct, right?
Sir,
So
it's
essentially,
valid for 2p,
yeah,
what you did.
exactly, right? So p, 2p, 3p, dot, 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 p square, right? So the number which is prime to this is 1, 2, dot, 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 p minus 1. Similarly here, p plus 1, dot, 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 2p minus 1, dot, 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 p square minus p plus 1, comma, dot, 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 p square minus p minus 1, and p square minus 1 and p square. Okay.
Yes.
So each of these are p minus 1 times p. Okay? So these are the total number of elements which are co-prime to p square. Right? In other terms, if you look at it, p square, phi of p square equals to p square minus p, right?
Yes, sir.
Similarly, the argument that we gave can be generalized to, in fact, it can be also be done using induction, right? That we know, we have proved it for power of p which is 1, we have proved it power of p which is 2. Let's assume this is true for phi p to the power k, which would be p to the power k minus p to the power k minus 1, right? So let's assume this. So what would be the phi p to the power k plus 1? It should be p to the power k plus 1 minus p to the power k. Okay. So one can actually do it using induction. Okay, but we are not going to discuss it. We actually will cover something which are more deeper. Okay, but this can easily be done using induction. So the idea is this is the final formula. Okay, which means p to the power k 1 minus 1 minus p. Okay, clear?
Yes.
Okay. So now the idea is, so this is Euler's Totient function, right? So phi of p to the power k is, can be given as this. Okay. Now let's look at this multiplicative property. Okay. It is very important. So think of it this way. Let's assume, let's look at 3. 3 is co-prime to 7, correct?
Yes, sir. By the way, what is the exact page number you are writing all this on?
Yeah, so this is like Euler's Totient function 201.
Yes.
Okay. Yeah, so the idea is 3 is prime to 7. Okay. Co-prime to 7. But 3 is also co-prime to, let's say, 5. Right? Which means 3 would be co-prime to 7 times 5, which is 35. Is this clear?
Yes, sir.
This is clear, right?
Yes, sir.
Yeah. So that's what this theorem tells you, that we can actually use this property to, so what we did is this. Earlier we said phi of p is easy to calculate. Then we derived a formula for pi of p to the power k. Now we want to get the formula for any composite number n using, we know that any composite number n can be written as a product of primes. Correct, right? We know that, right? So this is something that we should always use whenever we want to prove in general about a composite number. Decompose it into primes and then use the properties about prime to prove the property about the composite number. Okay. So this theorem essentially says that phi of n equals to phi of the product, right? But this can actually be written down it as k phi of pi to the power alpha I. So this is what this theorem is telling us. We can take the product out. Okay. But why is that possible? This is possible because, so let's do it for 2 primes. Okay. So let's say 7 and 5. Okay. So let's assume phi of 35. Okay, let's calculate this phi of 35. So you will see, let's look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and similarly others. So obviously these numbers are not there, right? So anything which will be co-prime to this will have to be co-prime to both 7 and 5. Correct?
Yes,
Because
sir.
the whole idea is any number, any prime which divides n. Let's assume there is a prime p which divides n, right? So any number that is a multiple of p will also not be coprime to n, right? Is this clear?
Yes, sir.
Yeah. And vice versa. Okay. So idea is that, yeah. Yeah. So let's look at this, right? So for phi n, this becomes the formula. Okay. So phi of n can be written down as this. Can be written down as this. Okay. Clear?
Yes,
Sir,
sir.
Any
I'm
questions?
unable to understand some over devices in the whole. Uh, like,
No,
how is this?
because we took n out, right? So phi of p1 to the power alpha 1 is what? p1 to the power alpha 1, 1 minus 1 over p1, right?
Yes, sir.
Similarly, p2 alpha 2 is 1 minus 1 over p2. So
Yes, sir.
this product of this equals to n. So n is out, and this is a product of this 1 minus p2, 1 minus p2, 1 minus p3. Clear?
Yes, sir. Yes.
Yeah. So idea is that what we just discussed gives us an idea that how to calculate Totient function for any composite number n. And this is possible because n can be decomposed into primes, and any number will be co-prime to n, will have to also be co-prime to all of its constituent primes, and vice versa, right? Any
Yes.
number which is co-prime to all the prime factors of n is co-prime to n, and vice versa. Any number which is co-prime to n will have to be co-prime to all the primes in the prime decomposition of n. Clear?
Yes, sir.
Yeah. So that's the main idea. Okay. And because we know the formula for pi to the power alpha I phi, so because of this mapping, right? So we know this formula, we just multiply it. Okay. So this helps us because now we can easily calculate phi of 36 and all those things, right? Okay. So let's take this example. 1000. So let's assume someone tells you, give us all the positive integers less than or equals to 1000, okay, which are not divisible by 5, 7, or 11. Okay. Which means what? We are looking for all the numbers which are co-prime to all three, 5, 7, and 11, and less than 1000. Which means we can just directly look at what is phi of 5, comma 7, comma 11. Right? So 35 times 11 is what? 350 plus 35, which is 385, right? So we know that phi of 385, if we can calculate, we are good. This is very easy to calculate. Why? This is 385 times 1 minus 1 by 5, 1 minus 1 by 7, and 1 minus 1 by 11. Correct? Correct,
Yes,
right?
sir.
Or 5 minus 5 to the power 0, right? Times 7 minus 7 to the power 0 times 11 minus 11 to the power 0. Correct? Remember the formula p to the power k minus p to the power k minus 1. Right?
Yes,
So this is 4, comma 6, comma 10, right? Which is 24 to 40. Okay.
yes, sir. Sir, for calculating all the prime numbers before 1000, I think we have to multiply it three times or something like that.
Yeah. See, this can be done via inclusion exclusion. Okay. But there is an interesting thing which we have to understand, and which is this. So see, we know all the total number of primes is this. Co-primes are this. Correct? So we know from 1 to 385, total number of numbers which are co-prime to 5, 11, and 7 are 240. But hey, we don't know starting from 386. Correct? So double of 385 is what? 760, 770. Correct? So
Yes, sir.
386 to 770, what is that number? How many numbers are co-prime to 5, 11, and 7?
Sir, 240.
And that is a very crucial property that you have to understand. It means it essentially forms a cycle. Okay. So any number I, let's assume, less than 385, if it is co-prime to 385, then 385 plus I will also be co-prime to 385, which means will be co-prime to 5, 7, 11. Okay. Why is that? Why is that?
Because it is co-prime to their products.
No, it's very simple, right? Let's assume not. Let's assume not. Let's assume I is co-prime, but 385 plus I is not co-prime. It means what? 385, there exists some prime P that divides both 385 and 385 plus I, which means what? Which means what?
Sir, I is divisible
P.
by either 5, 7 or
Yeah, so
11.
P divides I, right?
Yes, sir.
Which is a contradiction.
Yes, sir.
Yeah. Okay. So that's the idea. Idea is that it forms a cycle. So now you don't have to calculate this. So now you know that from 770, 240 times 2 are co-primes, which is 480. Okay. So if it were very easy, if the number were given 770 and not 1000. Okay. The same thing
Yes,
we
sir.
can do again. 770 plus 385. What is this number? 5, 5, this. Correct?
Yes.
So now we know that in 1155, 240 times 3 are the numbers which are co-prime. But now we have to subtract all the numbers which are 1155, which are divisible by 5, 7 or 11. Okay. So numbers between 1001 and this. But again, the good part is using the same logic that we discussed earlier. We can again translate this to what?
Another formula.
No, I mean, we can again shift this to, right? This is how many numbers? 155, right?
Yes,
So
sir.
we can do 385 minus 155, right? So because it's a shift, we can bring it in the range of 0 to 385. You understand what we are saying?
No, sir.
Okay. So see, this is the way of tackling large numbers. See, what earlier we had shown, if I is co-prime to 385, then 385 plus I is also co-prime to 385. Correct?
Yes, sir.
Yes.
But it also means the reverse as well, right? If 385 plus I is co-prime to 385, then 385 plus I minus 385 will also be co-prime to 385, correct?
Yes, sir.
Yes.
So that's exactly what we are doing here. So now what we are saying is, hey, 1155 or whatever that number was, right? And we
Yes, sir.
know,
1155.
and 1001, 385, which means what? We can subtract 1001 minus 385 times 2, which is 770. Correct?
Yes, sir.
So what will this number be?
Sir, 831. Sorry, 330, 231.
Correct, right? So 231 to 384. So this is the range we want. So idea is that we have to find all the numbers between 231 to 384 which are co-prime to 385. We get this number, we subtract this from 240 times 3. Clear?
Yes, sir.
Yeah. So idea is that, I mean, this is what we have done here. Okay. So this cycle, so you understand we are forming this forms a cycle. Do you understand that part?
Yes, sir.
So this, remember this property, this is extremely crucial.
Mm.
Okay.
Yes, sir.
So we learned two properties. So we learned two really important properties, which is if a number is
Co-prime to
if a
the
number is
factors of
co-prime
it.
to n, if and only if. So do you understand this notation?
Yes, sir.
Okay. So do you understand if and only if?
Yes, sir.
Yes.
Yeah. So co-prime to n, if and only if they are co-prime to all the prime divisors of
And
n. Okay. And the second thing is cycle formation. Okay. The idea
yes,
is cycle, form a cycle. Okay. You can just quickly shift I to I plus n, whatever the n is. And if it is divisible by, if it is co-prime to n, it will remain a co-prime to n. If it was not co-prime to n, it will remain the not co.
Not co-prime.
Yeah. Okay. So this is extremely crucial. Okay. Okay, so now let's come to this important theorem. Okay, let's come to this important theorem. Okay, so what does it say? So given a number n, let's look at all the divisors d of n. So let's assume 12. So what are all the divisors of n? 1
1,
divides
2,
12, 2 divides 12, 3 divides
3
12,
and 4,
right? 4,
6 and 12.
right?
6 and
So
12.
these numbers, okay? These are the divisors, right? Of 12.
Yes,
Divisors
sir.
of 12.
Okay. Now, important thing which you have to understand is this. So see, this formula seems very complicated, but it is not. It is very simple. Okay. So the idea is this. Think of it. If, let's look at this. If 3 divides 12, okay,
Then 12 by 3 also divides 12.
yeah. So then the quotient, what is the quotient? Quotient is 4.
4.
So then 4 also divides 12. Think about it. Why is that possible? Why is that true? If 3 divides
Because
12,
quotient is
yeah, go on.
because quotient is also the divisor of 12.
Yeah, because by definition, by definition, it means because the remainder is 0, right?
Yes.
Exactly. So if d divides n, it by default
Then n
means
upon
what?
d also divides n.
Correct. So n equals to d times some d1, which means d1 also divides n,
N.
right? So the idea is
So
the
basically, the
idea
LHS and RHS are both same. Basically,
equivalent,
both are.
correct,
Yes, sir.
correct. Because it's a one-to-one mapping. We can just simply replacing d by d over n because it's just a rearrangement of the sum.
Yes, sir.
It's nothing more. It's just a rearrangement of sum.
Rearrangement.
Okay. So this formula seems complicated, but it's not. It's just all it says is that, hey, we are just doing a rearrangement of the sum. Okay. That's it. That's what this formula is. And this formula is very important. It's called Euler's okay, sum of divisors. This is called sum of divisors. Okay. So this all were
Divisor.
this all were uh, okay. So right. So now the idea is this. Okay, idea is this. If this, so we are interested in what is this? Phi of d. What is this number? So we know that this number is nothing more different than this number. Okay. Okay.
Yes.
Yes. Now let's come to this. So we are interested in sum of all the divisors of 12, right? Which means this, correct? We are interested in this, right?
Yes, sir.
Important to notice that we also have 5 of 12. Why? Because 12 also divides 12. Okay.
Yes, sir.
Right? And you see this is symmetric. 12 and 1 equals to 12. 6 and 2 equals to 12. 4 and 3 equals to 12.
12.
Because of what we just discussed. Okay.
Yes, sir.
Okay. Now realize that there are 4 numbers which divide, which are co-prime to 12. So hence this is 4. Okay. Okay.
Yes, sir.
Okay. With 1, there is only one number which is co-prime to 1, which is 1. Okay.
Yes, sir.
Yes, sir.
Mm. With 1, there is only one number which is co-prime to 1, right? And less than equals to 1. 5. What does 5, 1 means? All the numbers less than equals to 1 co-prime to 1. Right? So it's 1. So
Hello,
the main
sir.
idea.
Hello.
Yeah, go on. Yeah.
Sir, only I am only looking front page of the book.
Mm-hmm.
Not anything. I mean,
Sir,
what you are reading, I cannot understand.
sir, that is why I asked you what is the page number actually, and I can
Only
understand.
looking the
Uh,
front page number of the book, not anything else.
you should
So
go
you are
to
not able to see
204
anything?
page.
No, I'm sharing a screenshot of this
Go to
on
204
WhatsApp.
number page.
204. Yeah.
But
There is an option above
how
the
do I
page which
go?
shows the page number.
Is it clear?
Only there is only one, the front page only.
No, you have to download the book. Did you download the book or no?
On Zoom.
You can actually sign in the website. You can go and sign in using your Gmail. It will let you download the book for free.
Which website?
Yeah, so this website, the Banyan Tree Book.com.
First I will sign, then it will show the book.
Yeah, so you sign in using your Gmail, it will let you download the book for free. Yes. Clear?
Yes.
Okay, so let's come back to this. Okay, so you can download the book when you're free and go through it. Okay. But is it
Sir,
clear what we
actually,
discussed up until now? Or any questions?
sir, actually, the book you are using to, screen share is not actually, when you are changing the pages,
Hmm.
the book present here on our screen is not changing the pages. So it is still on the front page. And I
Yes,
noticed that
it's
I
not
can change the
changing.
page.
Oh, okay, it's not changing it. Okay.
Yes, sir. Sir, but I noticed that the page number can be changed. there is a control option above the book. So from there we can change the page number, kind of go to page number 2, 3, 4, anywhere. So she
Oh,
should
okay. So you are saying that
bring.
even though whatever I am writing, but were you able to see my writing, or were you also able to not see my writing?
Yes, sir, writing is visible.
And we are only able to see writing. Writing is visible, but not the page number is.
Oh, okay, okay,
But when
okay. That's what you're saying. Oh, okay, okay, okay. Okay, I don't know how it worked. Okay, so then, okay, so in that case, let me, but whatever we discussed up until now, is it clear?
Yes, sir, clear for me.
So is it clear for YouTube or no?
not clear.
Not clear. Okay. So see, what part was not clear? Was it, I mean, so earlier we discussed the coprime part. So is
Yes,
the
that I
coprime
understand.
the cycle part? Did you understand the cycle part?
Yes.
I plus 385. If it is coprime, then it will also be coprime. Did you get that part? Hello. Hello.
Yes, sir.
Now I'm in the to.
Yes, sir.
Okay. So okay.
Sir, can you please ask them to, sir, they can try scrolling the page number. Sir, there is a
Mm.
option uh, just above the page page of the book where there are two buttons like arrow marks.
Mm.
When like you know how to skipping kind of arrow marks, so we can actually click them to go through pages. So they
There
should
is
do
no
that,
page
and
number option.
you can click on the book and then the option will appear.
Not appearing. Wait, I'm sending.
Okay.
No, I mean, did you download the book?
Yes, I download and also sign in on the website.
No, did you download the full book?
Yes.
Yeah, so then the arrow would work, right? I mean, it's just a PDF.
No, sir, she is talking about the book you are using on Zoom.
Oh, okay. Sure.
I
Let me
send in the
upload.
group.
No, it's okay.
Only looking the first page.
Okay, so
Did you
next time
try
I'll
to
be, yeah, next time
scroll
I'll be
that?
careful. Okay, I didn't realize. Okay, but idea is that which page do you see? Do you see, what do you see now?
Sir, page number 4.
First page.
Do you not see anything
Sir,
called prime factorization, etc.? You don't see anything like that?
No.
Okay,
No, sir.
sure. Okay, so let me, I think, probably use some other tool. Okay, so essentially, okay, probably that's the problem with uh, Zoom whiteboard, I guess. Okay, so let me go to files. Let me open the book here. Let me share the book now. I think now it should be visible. Yeah, because earlier I was not doing screen share. Okay, so that was the reason. Do you see it now?
Yes, sir.
Do you see page 1?
Yes.
Yes, sir.
Yes.
Okay, so let's assume I changed page. Did you see the page change?
Yes.
Hmm?
Then first page only. Yes. Now I can see the page change.
Okay, yeah. So my mistake, I wasn't doing a screen share. Okay. So do you see the screen share?
Yes.
So we understood. So idea is that okay. So my mistake. So sure. So the idea is this, right? What we said is that we discussed up until now. So we discussed this, correct?
Yes.
All of this was clear, right? P
Sir, could you
2P.
again explain the cyclic part?
Yeah, I'm coming to that. But all of this clear? P, 2P,
Yes.
3P,
Yes.
dot,
I
dot,
have
dot.
read this already, so this part is already clear.
Clear, right? Okay.
Yes.
So the idea is, yeah. So so the idea is that let's come back to this example. Okay, so this is what we were discussing. So it's clear, right, that phi of 36 is this. How did we arrive that? Clear, correct?
Yes. Yes, sir.
Okay.
Yes, sir.
So what you're saying is what is not clear is this part, right? So all we are saying is this. The
Yes.
question says find all numbers less than equals to 1000.
Which are co-prime to 5, 7, and 11, I think.
Correct. 5, 7, 11. So what we said is that we can use this formula, right?
5, 3, 4.
Right. So this is phi of 385 equals to phi of 5 comma phi of 7 comma phi of
11.
11. But what is phi of 5? It is 5
5
minus
into,
this, right?
yes.
P to the power k minus p to the power k minus 1. So this is 4, 6, 10. Okay.
Yes, sir.
This is 240. Clear?
Yes.
Okay. So if this is 240, then we know that, hey, we can do I plus 385. Will also be co-prime or non-co-prime based on what I's status is. Correct?
Yes, sir.
Clear?
Yes, sir.
So 385 times 2 is 770. So we know out of 770, 240 times 2, which is 480. So 480 out of 770 is co-prime. But we don't have to get it from 1000, not 770, which means 385 times 3 is 1155. Okay. So we have to subtract. So we know 240 times 3 is the total number of coprimes within 1155. Correct? So then we have to say what is the, we have to subtract. So this is cycle. You see, now we did not have to do any calculation. All we just saying is that shift I by 385. So this becomes a cycle, right? The same number now repeats.
Yes, sir.
So that's the whole idea behind cycle. Clear?
Yes, sir.
Yeah. Okay. So that's the whole idea. And that's where the whole. So what does it tell us about congruence? What does this tell us about congruence? Look at this. So we are saying I plus 385 GCD, comma 385 remains same. That's what our claim is, correct?
Yes, sir.
Equals to GCD of I, comma 385. Correct?
Yes, sir.
Is this a statement true?
Yes, sir.
Right? I mean, this can be proven using this. So if P divides, let's assume P divides, let's assume D is the GCD of I and 385. Okay. Let's assume this. Let's assume D is not a GCD of I plus 385, comma 385. Let's assume not. Which means there must be some other D. Okay. So now we know that D divides I, D divides 385, which means D divides I plus 385. Correct?
Yes, sir.
Yes.
So which means D is a common factor of, so D will be less than equals to GCD of I
I
plus
plus
3,
385.
comma 385, right? So
Yes,
let's
sir.
assume there is a number D1 greater than D, which is this, which means D1 greater than D divides I plus 385 and also divides 385, which means D1 divides I and D1 divides 385. Correct?
Yes.
which means D1 is greater than D. So D can't be the GCD, right? Because there is another D1 which divides both I and 385. So a contradiction.
Yes.
Clear?
Yes.
Yes.
Yeah. So that's the idea. So this is which means what? That if you are dealing with a congruence of any composite number, any number, composite or prime, the co-primes form a cycle. Correct?
Yes.
Yes, sir.
Hmm? Clear?
Yes, sir.
Yes, sir.
Yeah. So this is an important property. Yeah. So idea is that using that we can actually calculate that hey, 1155 has 240 times 3 coprimes. But the idea is that we have to calculate prior to 1000. So which means 10012 1155 is extra. But this is a large number, 385. So we have to subtract which ones are primes, or which ones have GCD greater than 1 with 385, or which ones are essentially divided by 5, 7, or 11. But this is a large number, right? So divide by 5, 7, or 11 is more difficult. Correct?
Yes, sir.
So then we can divide minus by 385 by 2, because as we said, GCD remains same. So we can just minus. So 1001 minus 770 is 231, right? So 231 to 384 is something that we are interested in. So yeah, I mean, find all the numbers which are here, which are
Co-prime.
co-primes, which are essentially not
225,
co-prime. I mean,
7.
essentially, yeah, co-primes. Okay. So this is like a, see, this problem can also be solved using exclusion, inclusion, right? Inclusion, exclusion. But the idea is that we are not solving it. This is another way of solving the same question. Clear?
Yes.
Okay.
Yes.
So now we were discussing this other interesting property. So so an interesting property of is this. So earlier we discussed, so we discussed, right? If D divides N, then N by D also divides D. Why? Because because N by D is also a quotient, right? I mean, N equals to D times N by D. Okay? So if D divides N, N by D also divides N. So which means what? This equation is just a rearrangement of the divisors. Correct?
Yes, sir.
Yes.
So this theorem says sum of divisors is that sum D by N phi of D. So N can actually be written down in this format. That is the whole idea. Okay.
Yes.
So yeah. So this is the whole idea. Clear? Hmm? So this part clear?
Yes, sir.
Okay. Now the idea is this. We have to work with this. Okay. Now let's look at this. Phi of 12, let's assume. Phi of 12 we already saw, it is 1, 5, 7, 11, which means 4. So phi of 12 is 4. Okay. Clear?
Yes, sir.
Right. Now each of these numbers have a GCD of 1 with 12. Correct?
Yes, sir.
So if we look at phi of, as we discussed here, d n by d. So let's look at phi of 12 by 1. So this is 12.
512, sir.
Sorry? Sorry, what? You have a question?
Then maybe she's speaking to somebody else.
Okay. Okay. So this is phi of 12, right? So now let's look at reverse. Phi of 12 by 12, which is phi of 1. Okay.
Sir,
Yeah, go on.
sir, the equation you're talking about, so so you have explained it 2 times, so we kind of understand that. Sir, we kind of know that if like how this works. So
Okay,
so
so
I
you know
think
that,
we
right?
need to, yes, sir, for 12 or any number. We
Yeah.
no, we don't need examples, sir.
Okay, okay. So you understood this, right? Okay.
Yes, sir, yes, sir.
So idea is that this is just a rearrangement, right?
Yes, sir.
But now the idea is that what we are trying to understand is how this sums up to n. Okay.
Yes, sir.
So why this equals to n? Because this essentially forms a set. So let's look at this. Let's look at any divisor of n. Okay.
Yes, sir.
So what is n? N is, let's say take the example of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Correct? There are 12 numbers. Right?
Yes, sir.
Now look at phi of 1. So phi of 1, which number will be co-prime to 1?
Sir, one only.
1. Right?
Yes, sir.
Correct? Let's look at phi of 2. Which numbers are co-prime to 2?
Sir, one.
1. Okay. Which numbers are co-prime to 3?
Sir, one and two.
Right? So this is the count. So if you take a
Yes,
count,
sir.
it will be exactly 12, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay.
Mm.
Why is this happening? This is happening because if you look at all the numbers which are co-prime,
Mm.
okay. So now let's look at this. All the numbers which are co-prime to 12 are this. Okay.
Yes, sir.
All the numbers which are which has a prime of 2 with 12, GCD of 12, are this. So see, you take
Yes,
any
sir.
number, they can either have a GCD of 1, 2, 3, 4, 6 or 12 with 12, correct?
Yes, sir.
There are no other options, correct? Which means
Yes, sir.
all the 12 numbers can be broken down into these 6 sets, correct?
And there are exactly 12 numbers in the addition, in the summation of the orders of the set.
Yeah, so now the idea is this 1 corresponds to 512. This 2 corresponds to 5, 6, right? Why?
Yes, sir.
Why is it 5, 6? Because see, 12 by 2 is 6, right? So all the
Yes, sir.
numbers which form, so let's look at this. What are the numbers which form GCD of 2 with 12? These numbers are 2 and 10.
Yes, sir.
GCD of 2 between any number. So that's 2 and 12, 10, right?
Yes, sir.
Correct? So now if we divide this 3 by 2, so it means what? 1 and 5 are co-prime to 6, correct? So see, the
Yes, sir.
count remains the same. It's 2, 2 by 10. Point is that you have to just divide this by 2, which is the GCD. It will become it will give you the count of 5, 6. Clear?
Yes, sir.
So idea is that you have defined the GCD, it divides the set, and all you have to do is that this is just a remapping of 5, 6. The count remains the same, just the number 2 and 10 changes to 1 and 5. Here, 4 and 8 is 5, 3, which is 4. So which means 1 and 4. 12 will becomes 1. Clear?
Yes.
Yes, sir.
So do you understand why is it n equals to 5? I mean, why does that equation hold that we discussed earlier?
Yes, sir. I got it.
Yes, sir.
Yeah, so essentially, so this is a, put this into mind. Idea is that this equation is very important because it's just a rearrangement. So this part is clear. This part is simple. This is simple. What is not simple is this part. That essentially, when you essentially look at all the numbers in terms of GCD, it forms a set. And now this set directly maps to this. Okay.
Yes, sir.
Clear?
Yes, sir.
Yeah, so this is the most important property of
Gaussian function.
Euler's Totient function. Correct. Okay. So let's yeah, so idea is that that's the idea. So this is the final equation. This is just what we prove. Okay. Yeah, I mean
Yes,
all
sir.
positive divisors. I mean that's okay. So this is a more
Mm.
comprehensive proof here. Okay. And now Euler's theorem. So Euler's theorem tells you. So let's discuss Euler theorem in the next class. Okay. But the idea is this chapter is the most important chapter. If you understand this chapter well, I mean, I think most of the questions comes from this chapter. Okay. But let's discuss the problem that we discussed last time, that was given last time. So were you able to solve it or no?
So some of them.
Yeah, so but you could solve both of these, right?
This is
These
solution.
three problems. Were you able to solve all these three?
Yes, sir.
Okay.
And sir, there is doubt in one part in problem 2.
Okay. So what is the question?
And in problem 1, the E part,
Or problem
I
one.
wasn't able to do.
Or problem 1E.
Yes.
Okay. 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 Yeah. So what does it say? Prove that for all n greater equals to 2, the coefficient of this.
Of x part n minus 2 in P and x equals minus of n minus 1.
Yeah. Were you able to prove up to ABCD?
What? Yeah. Up to ABCD. For D, I did with induction.
Yeah.
And F part is only the arithmetic AMGM inequality. Yes.
Correct. So I will send you a solution to E. Okay, but you were not there last time, so let me describe again AMGM. 5 minutes, and then we will, I think, we will call it a day for today. Okay. So
But,
see in AMG,
in
yeah. So I will send you a
in
solution to
problem
E. Yeah, go on.
in problem 2, the first problem part A, in which we have to determine the alpha plus alpha dash and beta plus beta dash and gamma plus gamma dash in terms of A B C D E F. The solution you provided in this, I have doubt in the solution you provided.
Okay. So see this. Okay. Here's the thing.
Part A.
Yeah, part A, correct. Okay.
It's
So
just
this is how.
simple, but manipulation is the main key.
Yeah. So here's the thing. Okay. So I will. Here's the thing. So let's break it down. Okay. So this is alpha, beta, gamma, right? Okay. So tell me, how many coefficients will be there?
There will be
So how many, if
Really.
when we expand this term, how many coefficients will be there?
nine. There will be
Are you
9
sure?
terms.
Are you sure?
8 terms. 8 terms. Sorry.
Why would that be 8 terms?
I just multiply to that.
No. What is the mathematical logic to have 8 terms?
There are 3. We are multiplying 3 terms. So first we will multiply 2 of them. Then we will get 4 terms. Then with 2, 4 and 4,
Yeah.
8.
So essentially, in combinatorics, you have two choices from here, two choices from here, and two choices from
And
here.
2 choices from it.
So 2 cross 2 cross 2, 8. So that's why
2.
you get 8 terms. Okay. So that's the logic. Clear?
The solution you provided there in this,
Okay, so
what
I
did
will,
you
I
do?
will,
I
I
can't
will.
understand in that.
Yeah. So the idea is that see, I mean, this is simple. I will check in case I might have done some calculation mistake. But the idea is that
No,
you do
sir. There
understand.
is no mistake actually, but you have actually not shown how the equation was, how the like when we opened this a alpha plus alpha dash, and this whole thing when was opened, we had no idea that how we
Where gone the
have
terms in
actually we
Yeah,
had
go
no
calculator?
on.
idea how to
Mm-hmm.
manipulate it in such a way that we can bring A, B, C, D, E, and F into it. We were only able to see that C and F are directly I mean
So
easily
what you're saying
possible
is that,
to
okay, so what you're saying is that the solution is not very comprehensive, correct?
yes sir.
Okay, so what I will do is that I will
Where
revise
gone the
it to
term
make
which
it
is
more
in
comprehensive so
subtraction
that you can
in your
see
solution?
how. Okay, so I will send you a revised solution, breaking it down more appropriately. Okay,
Yes sir.
okay. Anything else?
In the problem was out of scope of ISI.
Which one?
You tell it. Problem 4.
Yeah, problem four. Yeah, I removed it, right? Problem four. Yeah, it was a little bit more advanced. Yeah, some part of it was
Uh,
within the scope, some of it was not. Yeah, so okay.
I did 3 of them,
Mm-hmm.
which
Yeah.
the finite difference method I have studied about with the help of that.
Mm. So let's discuss AMGM. You are not there, but I think it's important that you understand. Okay. So see in
Okay.
AMGM, this is arithmetic mean, right? Given x1, x2, dot xn, summation xi, 1 by n. This is arithmetic mean, correct?
Yes. Yes.
This is greater or equals to x1, dot xn, right? So what does arithmetic mean say is that the equality holds if all the xi's are
Equal.
same, right? Equal. So let's assume the moment we change some xi plus epsilon and xj minus epsilon, the arithmetic mean remains same, correct?
Yes, sir.
But then what should happen to the geometric mean?
Symmetric mean will decrease.
Decrease. Exactly. So point is that that's what AMGM says. If you're keeping the sum of this constant, geometric mean
Is
reaches to the
decreasing.
maximum potential only when they are all equal.
All xi's are same.
Yeah, so which means what? The graph of geometric mean should look something like this. Here, this is a
Parabola.
boundary and this is the arithmetic mean. Okay,
Yes, sir.
and this becomes maximum only when this.
Only when all
Similarly, the
xi's are equal.
similarly the reverse. Let's assume what you do is that divide x1, all of them are equal. Now divide x1 by 5 and x2 by 5. Geometric mean remains same, correct?
Yes,
But what will
but
happen to arithmetic mean?
arithmetic mean it will.
Because there is no equality, it means arithmetic mean will has to increase, correct?
Yes, sir.
So which means what? Geometric mean is a lower
Constant.
bound, lower bound for. So this is what arithmetic mean looks like while keeping the geometric mean constant. In that terms, arithmetic mean will continue to go up, and this is the boundary of arithmetic mean. Geometric mean is the lower bound. Okay,
Okay.
clear?
Yes, sir.
Okay. Yeah, so what I will do is that I'll send a revised solution to one and those two, and then in the problem set 2, how many were you able to solve?
These problems are tough. I mean, for me at least, I am not that good in number theory. I just do IOChem level problems, able to do, and some of RMOs.
Okay. Yeah, but do try.
In problem number 1,
Hmm? All right, is it clear?
yes,
Hello.
yes,
Okay, so
sir.
do try. What I will do is that I will do try. If it's difficult, sure, then it means that you
If I'll
need.
ask in the group, could you only explain the hint of the problems? How to start even some of them?
No, so see, I mean, this problem is about totient function. If you don't understand totient function, then you won't be able to solve it.
Mobius inversion is also included in this.
Yeah, yeah, so if you, the idea is this, right? I mean, if you don't know these things, then you won't be able to solve it. I mean, it's as simple as that.
No,
So
I
first you
know
have to
those
know
things.
them, right?
Yes,
Like for instance, here, it's so this is very related to what we just discussed now. K equal to 0
yes,
to n, phi p to the power k, right? And then it says that find a closed form for Tn. So
yes.
yeah, I
This one
think,
I did, and I got limit as 1.
yeah, so then probably you did something wrong. Probably check that. Okay.
Okay.
Yeah. I mean, tell me how this would work. This is actually telescoping the series. Do you understand what telescoping a series is?
Mm.
So see, what is what is 5p to the power n, right? The biggest term
P
is
to
p
the
to the
power
power n,
k.
correct? This is
It will
p to
go
the
P to
power
the power
n
k
minus
minus
p to the power n minus
P to
1,
the power
correct?
n minus 1. Then next term is for so
p to
this
the
will
power n minus
come out
1
well.
minus p to the power n minus 2,
Minus P
correct?
to the power n minus 2.
So it will
Yes, and
cancel
it will
out,
cancel
right? So
out all.
yeah, so what you will be
Mm,
left with is p to the power n
P to the power n
minus,
minus
yeah,
probably 1 5.
yeah, I think I also think so. Yeah, I mean essentially, phi of p will be p minus 1, right? So pp will cancel. So phi of 1 will be 1. So this, no, so it will be essentially be only be
1.
correct. So I think this is probably there is some wrong here. Yeah. So this you are correct. So this is essentially p to the power n because everyone else cancels out. Yeah. So but then so TPN, yeah. But yeah, let me solve this properly. Okay.
Okay, sir.
Yeah. But the idea is that, see, yeah, main idea is that, yeah, I mean, see, if there are some typo, some mistakes, that's a different thing. But idea is that as long as you understand the concept, that's all we care about. Okay.
Uh, Okay, sir.
Yeah. So let me check and then I will come back on this. So let me first check the solutions to the previous one, and then if there is some issue with this, then I will revise it. Okay.
Okay, sir.
Sure. Anything else? Any questions?
No, I am not able to attempt all the problems, so I'll send solution in the group, the group on WhatsApp.
Yeah, no, but the idea is that you shouldn't see the solution. See, idea is that if you don't even know the theorem, then what's the point of even seeing the...
No, I know the theorem, so
Okay,
I
okay. Yeah, so
attempt
then
some
you
of
go
them.
ahead and see it. Sure. Yeah, then I will obviously send the solution. Yeah. Okay.
Okay.
All right. Yeah. So anyone else? Jitendra, Anuj, anyone else? You have any questions?
No, sir.
Okay, sounds good. All right, so I
No,
think we
sir.
are okay. So I think we are uh, done for the day. Okay, and yeah, I think let's meet next week. Okay.